So if you speak about this electric field, I am imagining this cone-shaped electric field. Now when I say this, there is this cone-shaped electric field, what's happening here is the electric field lines would go like this. So the density of the electric field also reduces, the intensity of the electric field also reduces when we go from left to right, and the electric field lines are also becoming more spaced. Their density also reduces. Now I'm considering two different surfaces here. There are two different surfaces, surface 1, surface 2. Let me color this surface green. Let me go for this color here. This is the direction. Now let's look at this length. Let me consider this as R1. Let's consider this length as R2. Now there is an angle which we are making. This is not our usual theta, rather it is solid angle. Now solid angle, so if it is a linear angle, it is like this, it is on the same plane. But is a solid angle means you have to imagine a cone. So the angle, that's a three-dimensional angle which we have at the cone, that's a solid angle. So I'm considering that as delta ohm. Okay, this is my solid angle. Now if we have solid angle, it is the area of a curved patch from the vertex. I'm referring to this green and brown areas. So that can be given by simply squaring the distance of the curved patch, multiplying it by solid angle. We can find the number of lines that will be cutting that unit area, right? So we have the area here. I want to count how many lines would cut that area. Okay, now let's say the total number of lines, the electric lines of force is N. Now if you look at area 1, then that N is divided by some area. What is that area? Area I told you is given by distance squared. So R1 squared multiplied by the solid angle is the same. Now in the case of 2, the number of lines is the same. It just as the distance has increased, R2 squared multiplied by the solid angle. Now this gives me a very important thing. It is nothing but the density of lines of force. It is nothing but density of lines of force. But we already saw that electric field strength is proportional to the density of lines of force. We just saw that. So this is proportional to N into R1 square into delta ohm. Similarly, E2 is proportional to N by R2 square into delta ohm. Now if we express this as a ratio, E1 by E2, we will see we are left with only R2 square by R1 square. This shows us very important thing, that E is proportional to 1 by r squared. That tells us that electric field is inversely proportional to the square of the distance, which is a result we already know. We are going to speak about a concept called area vector. We'll see what is an area vector. Now let's consider a planar area. That means this area is present on a plane. So I will call it a planar area. Then let's consider a normal which I draw to this area. So I'll represent the normal as ds vector. It is the normal drawn to the area. Now this ds vector is given by ds into n cap. So this is called area vector. I am representing the area as a vector. So this ds gives the area and this gives the direction. N cap gives the direction. So what we have done is represent this planar area by a vector now. This is in the case of a planar area. Now let's look at what happens if it is a curved area. Now that is something like the surface of a sphere. Now if you have a spherical surface like this, a curved area, the surface is made out of many small planar area. Now this is a curved area. You have to imagine this to be made up of several smaller planar areas. So this is a small planar area. Now if I draw a normal to this, it goes like this. This is ds vector, which is also in direction of n cap. So it is the same. ds vector is equal to ds into n cap. That is for curved area.